Welcome, everyone. Welcome to Datadog on detecting threats using network traffic flows. Datadog on is a series where we invite engineers working on Datadog to talk to us about a specific technology or an interesting problem that they're trying to solve. The recordings for this will, of course, be available on datadoghq.com. Some quick housekeeping items before we start. This is a live presentation, and I'd love for you to interact with us here as we walk through the session today. If you want to let us know that you're here and you're watching this Datadog on session, feel free to say hi in the chat and just let us know where you're coming in from. Also be interesting to know, what are you interested in getting out of this Datadog on session today? Have you ever heard of VPC Flow Logs or network traffic flows before today? And please do use the Q&A feature in Zoom to ask questions as we go through. And I'll do my best to kind of surface those to our presenters today, who you're going to meet in just a bit. So with that, let's go ahead and jump into the Datadog on session. So if you've never heard of Datadog before, Datadog is a monitoring and analytics platform that helps companies improve their observability in their infrastructure and applications. And of course, you might be aware that recently we've also made a significant move into the security space, this marriage of the idea of security plus observability. And you're going to hear a lot about how we do that internally at Datadog today from our great presenters. I'm Andrew Krug. I am a security evangelist. These days, I'm the security evangelism and advocacy lead here in the community team at Datadog. There's my Twitter. And we'll go ahead and we'll get right to our amazing presenters. Anna, do you want to go ahead and introduce yourself first?
Yeah, hi, Andrew. It's good to be on this talk. I'm Anna. I've been at Datadog for a bit more than a year and a half now, and I'm on the threat detection platform team together with Théo.
Hey, everyone. Hey, Andrew. So I'm Théo. I'm a software engineer here in the threat detection platform team here since 6 months now. I'm working on security pipelines at large scale here at Datadog. And for me, it brings security to another level from a data point of view. And this is what I love.
Okay, let's get started. So what does it mean to detect threats? To define that, I like this little definition script. A threat detection rule is a script that detects malicious or suspicious behavior. So this rule contains the logic to detect whether the company has been compromised. It's essentially a query at heart that runs against any data source with security value. So that could be audit logs from cloud providers such as the AWS Cloud Logs. It could be DNS logs or network flow logs. And well, network flow logs is today's topic. In our internal security team at Datadog, we have a team of security experts that is responsible for writing these rules. Théo and I are software engineers on the sister team to help that threat detection team actually deploy, run, and scale these rules. Most of our detections already run against Datadog's custom product, but with the network flow logs, it's a little different because of the scale. So for a reference point, we ingest hundreds of gigabytes of uncompressed logs per hour just for the AWS network flow logs. And that is what we want to talk about today, how we can detect threats at the scale of network flow logs. Now, why do we care about network flow logs? Some of you might remember that last December, a zero-day vulnerability was found in the Log4j library, or more recently, also in the Java framework. So I'll go through the steps of a potential exploit of that vulnerability at a high level, and then I'll highlight where the network flow logs could be useful. So here you can see that step one, the attacker uses user input to pass a malicious payload. So that could be, for example, via the HTTP header. Then in step two, this payload gets logged with the Log4j library. In step three, that library interprets the code and connects to the attacker's malicious server, which is like referenced in the payload. And this is where the traffic logs can be useful. In your logs, you should be able to find that outbound connection to the malicious server. Then in step 4, it goes in the other direction. The malicious server sends back the response, telling the application to load a remote cloud. And this should again be seen in your network traffic logs, this time as incoming traffic. And lastly, the actual exploit happens when the remote Java class file gets executed. Now, that's just one example. There's many other exploits that can be identified with network flow logs. Now, you might already have some logging set up within your application to monitor who connects to your network, but the only thorough way to know who connects to your network is by collecting all network traffic logs. Yeah, I will now hand it back to Théo, who will introduce what network flow logs are, and specifically the AWS VPC Flow Logs.
Thanks, Anna. So before anything else, what are VPC? On the next slide, you will see that VPC stands for Virtual Private Cloud. It allows to isolate apps running in the cloud and also manage network access for inbound and outbound assets. On a daily usage example, VPCs are like your home Wi-Fi network, but without Wi-Fi and in the cloud. We have apps that are in a subnet and subnets that are inside the VPC. VPC and subnets allows us to isolate apps like a firewall. Isolation is great for security in general. And of course, VPC can have access to internet through a VPC gateway. What we want to look at in our example are interactions inside and outside of VPC. We will look at network logs between two subnets and between the VPC and internet, or another VPC. This is what is represented by arrows on this graphic. On the next slide, we will see how does a VPC log record looks like. The content of a VPC flow log, VPC log, is pretty simple, just like what we have here in this example. Some data are more important than others in each record. That's why we have sensitive data that has been hidden. Basically, a VPC log record describes a request between two resources and whether it has been accepted or not. The first item is a version. This is a version of the log record. Previous version has less information. Then we have the account ID, which is the AWS account ID where the request has happened. Then we have the interface ID, which is the ID of the Elastic Network Interface. An Elastic Network Interface is similar to your Wi-Fi adapter on your laptop, but it's running in the cloud. Then we have information about IPs and ports of resources involved in this request. Then the protocol ID, which is the Internet Protocol, which describes the protocol, UDP, TCP, SNMP, SMTP, or more. These IDs are defined by IANA, Internet Assigned Number Authority, which is a worldwide organization which defines some standards used by all IT systems. The action gives the information of the acceptance of the request. That's basically the result of the firewall. And finally, the log status, which is saying if the log record has been correctly logged into the sink. We will speak about that later. On this example, we can see two accept requests, which show two services discussing. IPs are hidden, but I can tell you they are the same. And we can also have a look at ports 443 and 3768 that are reversed, showing an inbound and an outbound communication using the protocol ID 6, which is TCP. Also, the port number 443 is mostly used by HTTP web services using SSL. So we can easily say with these logs that someone has reached a Datadog web SSL service with the time and its IP. and the service has answered to the client. So we want to make sure that all of our services are not reaching suspicious IPs, or suspicious IPs are reaching to us. So that we use VPC logs. As you can see on previous slides, we can easily find the inbound or outbound traffic of a request looking at the history of requests. And this is something really important for us. Of course, Datadog is available to anyone on internet, and we want people to be able to reach us. Of course, we don't want to be attacked. So if a suspicious IP is reaching to us, we raise a warning. And it's even more important for outbound traffic. In case we have an internal service reaching a suspicious IP, it means that we could have been compromised. And this is the base of VPC Flow Logs.
So Théo, can you tell us a little bit more about some of the things that somebody might do when they're connecting back out? You know, if you're compromised, like what would that be an indicator of?
It could be an indicator of someone at Datadog doing something suspicious, reaching a log4j server, for example, or an attacker that successfully compromised a server and using this server for malicious purposes. These are two threats that are coming to my mind.
Usually I think about data exfiltration a lot of times when I think about detecting things in flow logs as well. And for the folks that are just joining the webinar here today, you know, Théo did a great job of walking through kind of that format for the flow logs here. And what that really is at a very high level, if you missed it, is just it's the recording of all of the conversations that take place in these VPCs, which are that highest level unit in the AWS network stack, right? So that's like the entire network boundary. So we're recording that and we're matching it with threat information here, or a list of suspicious IPs. And I'm sure you're going to tell us a little bit more about how we get that list of suspicious IPs here in just a minute.
Of course we will. And before that, we will speak about the VPC Flow Logs by itself, because we know what are VPC logs right now and how it can help us detecting suspicious IPs, communicating with Datadog. But how do we set up a pipeline that can monitor that efficiently and, of course, alert us? So, as I said previously, VPC logging is showing all interactions between subnets or apps with other subnets or apps and internet. And fortunately, AWS provides a way to get these interactions with flow logs. That's why we speak of VPC flow logs. We can output them in multiple things, CloudWatch or S3. And due to the fact that we bring logs from various regions and accounts, we need to send them to S3, as this is a global service, in contrary of CloudWatch, which is a region service only. So we send VPC flow logs of all VPCs from all AWS accounts, from all AWS regions that we have at Datadog. And we send them to an S3 bucket that has been previously created. And as you can imagine, that's quite a lot of data. Hundreds of terabytes of logs per month. So how can we make sure we don't miss any VPC? For that, we use, so on this screenshot, you can see the AWS console, which is the flow log I was speaking about, that can forward logs from a VPC to an S3 bucket. The objective is pretty straightforward. For each of our VPC, we want to send data to S3. Simple as that. So we have a lot of VPC and we can't manually set this up. And to do that, we will automate this process using Terraform and code generation with templates. Few words about what this is first. Terraform is an open source infrastructure as a code software tool created by HashiCorp. To make it really quick, you define resources with some code, you give it a cloud provider, and Terraform will do the hard work of setting this up. Also, it's interesting for us because we want to use the possibility to reproduce a setup multiple times. And as this is code, we want to keep track of history changes of our setup. Code generation is done using CodeGen, a commonly used tool to generate code with Terraform. So let's have a look at that on the next slide. With these tools, we can generate whatever we want. We first start with CodeGen. We give three informations to CodeGen: all AWS accounts, all AWS regions, where we want to apply the third information, the template. We say to CodeGen to do a nested loop through all accounts and regions and generate a template for each of them. Each of templates have a specific information about the account and the region. The template, as we can see here, is a Terraform module, which can be seen as a Terraform function. This module is named VPC Flow Logging and is listing all VPCs in the given AWS account and region, and basically defines a sink, in that case S3, and other kind of information like filters, log format, traffic type, etc. So this setup is pretty unusual for Terraform, but we have to use it because Terraform does not provide a way to iterate on providers that are defining the account and the region where resources are applied. And basically, that's all. Only 20 lines of code. We generate hundreds of terabytes of logs every month. That's crazy. So now that we have all logs available in S3, how do we process them? And I will let Anna presenting you that.
Yeah, thanks, Théo, for that introduction on what VPCs are and how we get these logs. As Théo said, I will now talk about how we process the logs and how we run detections against them. In AWS alone, we have, as Théo alluded to, we have hundreds of VPCs generating hundreds of gigabytes of uncompressed logs per hour. To process these logs, we actually use Mortar, which is our internal service to process data at scale. Mortar is a company that was acquired by Datadog back in 2015 and is now used by the data engineering teams for various ETL purposes. I will go into the architecture in more detail later, but at a high level, we have a scheduled Spark job processing the data and running the detection. Processing the detection at intake time has the huge advantage of reducing latency and detecting a compromise as soon as possible. AWS itself has an SLA of around 10 minutes on VPC Flow Logs. So that part we can't control in the latency, but we can control how quickly we can run a detection once we have access to these logs. Now, how do we find suspicious traffic? We match the VPC Flow Log IPs against a list of suspicious IPs using Misp. Misp is an open source, or it stands for a malware information sharing platform that allows us to easily maintain a list of suspicious IPs. And Misp is open source and it's free to use. So if you want to, you can very easily add it to your own security system as well. On the slide, there's a screenshot of the Misp website and an example list of publicly shared suspicious IPs. Now, usually you don't go onto the website and copy paste the list. For example, we run an internal instance of Misp where we store the publicly and privately sourced indicators of compromise more generally, which include the suspicious IPs that we're using for this detection. Then we have that Misp Misp instance, but we also have a job that queries that Misp API, stores the list of IPs in an S3 bucket just to be a bit more accessible by the downstream jobs. Okay, so first I'll give you an introduction to the overall architecture, and then afterwards we will deep dive into a single job. So this is the graph that you saw before, where Théo introduced the VPCs, how they talk to each other and generate the traffic that gets exported to an S3 bucket. We then use AWS's notification system, EventBridge, to emit an event whenever an object gets created in that bucket. Note that that event only holds a pointer to the S3 file, not the actual logs. These events then get forwarded to the Kinesis stream, which is, as the name can tell, AWS's streaming service. The Kinesis stream holds these events in order of creation, and then our Mortar job reads from the Kinesis stream. It also uses checkpoints to pick up reading from where we left off. So that allows us to only read the events we have not processed yet. And yeah, so we store these checkpoints in DynamoDB, which is a lightweight database. Yeah, the processing job then also reads the Misp IPs that I introduced before from an S3 bucket, and then matches them against the IPs from the VPC Flow Logs. And then finally, if there are any matches, the job sends the log that matched with the malicious IP address to our alerting system to then be inspected by a security engineer. Now that is the overall architecture. I want to share a few notes about the design choices. So we use EventBridge because listing S3 files can be very expensive and slow if the data is not partitioned in a granular way. So in addition, it's also difficult to account for delays, because if we would have to list files for a larger time frame and then filter by the created at timestamp. Sorry about that. And that again makes it more expensive. Instead, we opted to use EventBridge, which allows us to keep track of newly created S3 files without worrying about delays or granular partitions. We chose Kinesis over other event processing solutions like Kafka because of its low operational costs and an easy integration with EventBridge. Another option would be to use SQS queues. Sorry about that. Still recovering from a cough, but I am excited to be here. Yeah, so I was just talking about Kinesis, and we chose Kinesis over other event-based processing solutions like Kafka because of its lower operational costs and its very easy integration with EventBridge. Yeah, and the other option would have been an SQS queue, but we opted for Kinesis since we wanted to have the option to have multiple consumers from the stream. And if we used SQS, then the event would have to be deleted after being successfully processed.
I think what's interesting about this architecture here is that we've kind of broken out every component that could be cloud native to a cloud native service, right? So like there's very few things here that are on EC2 instances. So from a security team like design perspective, there's almost nothing in this that has to have regular maintenance over time, which I think is really, really compelling to think about as you think about kind of like taking this and implementing it, at potentially companies that have very small security engineering teams.
Yeah, absolutely. Thanks. Yeah, so now let's take a closer look at the Spark job. So for a larger context, the data processing platform we're using, Mortar, is optimized for batch processing and not streaming. So therefore, we run a job every hour, making small batch requests to get events from Kinesis. So for someone else's infrastructure, a streaming architecture might work better. We also run the jobs on Spark, which is Mortar's data processing engine. Spark allows us to efficiently enrich the data and then also parallelize matching flow logs against malicious IPs. First, the first part, which is now visualized on the diagram, is actually reading the Misp IPs from the S3 bucket. Then that Misp data is broadcasted to all Spark nodes. So that means it's cached on each machine, and it can then be accessed more quickly by the tasks when they read the dataset. Then we get the latest checkpoint from DynamoDB. So that checkpoint is if you remember, is the point in the stream of events from which we want to start reading. So instead of starting to read all events from the beginning, we read from where we stood the last time. Quick note on that. So you can use two types of starting points to read from, either the timestamp or a sequence number. And if you choose the timestamp, it will use the approximate arrival timestamp, which by definition is approximate and not guaranteed to be in order if there are event processing delays. So therefore, we chose to use the sequence number instead, which is guaranteed to be increasing. But in practice, we haven't observed the timestamps not to be in order, but we wanted to be safe. And we store them in DynamoDB, which is just a lightweight NQL database, and we use it to store a key value pair, mapping the Kinesis shard ID to the checkpoint. So you could use any other storage option for that as well, but DynamoDB is the recommended solution for Kinesis. Now, let's talk about Kinesis. As I just mentioned, we map a shard ID to a checkpoint. So when your Kinesis throughput becomes too large, you have to split the stream into shards, each of which then contains just a portion of the events. That means you also need to save a checkpoint for each shard. Yeah, and then starting from the checkpoint, we read a maximum of 10,000 events from the stream, which contain, if you remember, the pointers to the S3 log files, not the logs themselves. So basically, the goal is to catch up to the latest entry in the stream. And if we are all caught up and there is not much traffic, then we might process less fast. But if we fell behind previously and we are catching up, then we read a maximum of 10,000 files at a time. And we experimented with that a bit, and we just found that the job is most resilient and efficient if we batch reading from the stream into sizes of 10,000 events. Now, the next step is to actually get the files from S3 and save the logs in a data set. We then check for each log line whether the source IP or destination IP address matches against an IP address in the Misp dataset. And then if the IP address of a traffic log was present in the Misp dataset, then send this enriched version of the log to our alerting system. And then depending on the severity, the alert gets sent to a selection of Slack, PagerDuty, and email address destinations, as well as Jira to track the alert. And then our security engineers can take a closer look to evaluate whether the traffic is malicious or if it's a false positive. Yeah, and then lastly, we save the checkpoint in DynamoDB to update where the next job should pick up the work from. And we repeat that cycle until an hour is up and the job gets restarted. And so you see this, we call it a micro batch job because we have this, it's already a batch job because we run it every hour, but then within that, we make multiple batch requests to Kinesis, very much simulating a streaming architecture. Yeah, and I just want to quickly show you how our Mortar UI looks like. So you can see here that we, every hour, we start this new job. The job lasts roughly an hour, and we can see whether it succeeded or not. And if it failed, then we also show this, and hopefully the next job, when it starts again an hour later, can just pick up the work again. Yeah, to show you an example of an alert, I fabricated one just to demonstrate. As I mentioned before, we make use of Jira to track the alerts. And on the left-hand side, you can see a Jira ticket with the general description of the alert and a link to the response playbook. And the ticket itself also includes more details about the alert itself, which you can see on the right-hand side. So in the first box, you can see a description with details about the Misp indicator itself. It also mentions log4j here. And that is because after the log4j incident, we immediately added the malicious IP addresses as they became public to Misp. And we stored them in a separate list to be more easily identifiable as being related to the log4j vulnerability. And in the second box, you can see more details about between what IP addresses the communication happened. Yeah, managing these alerts in Jira allows the response team to really collaborate and keep track of the status of handling the alert. Yeah, that's it from me about processing the logs and running detections. Thanks for your patience with my coughs, and I'll hand it back to Théo now.
Thanks, Anna. So yeah, that's awesome. We have an efficient pipeline that can process hundreds of terabytes of logs per month, allowing us to monitor the network flow logs of Datadog. And of course, send alert when a suspicious IP is detected. As you can imagine, we are at Datadog. We love monitoring. And of course, we monitor or monitor. That's why on the next slide, you can see the number of S3 files. So this is a custom metric for our pipeline. And for example, we have millions of files created in S3 from VPC Flow Logs. We run batches of 10,000 gzip files, which represent almost 48 seconds of logs during 1 hour long. And we process around 40 loops during an hour. So yeah, that's great. But this pipeline has one pain point. We ran some tests and we found that in case our pipeline is not working for a given time, it's really hard to catch up the delay it has created. And it could be a big threat in our system since because of this delay, we can detect an attack after a lot of time and this attack could be potentially finished. So we need to find a way to catch up really easily. Thankfully, in October 2021, AWS has announced that VPC Flow Logs can be saved in Pocket format. This was not supported before. In easy terms, reading Pocket files is faster than reading gzip files with Spark. This is basically due to the fact that Pocket files are saved by keeping the column structure of data. Also, Pocket files are bigger than gzip files, meaning we can have less event-rich notifications and fewer files, but we still have the same data. In addition to that, in our current pipeline, gzip files were saved as Pocket files for future investigation at the end of each microbatch. If we already have the data in Pocket on the inputs, we don't need to store anything on the output, which reduces a lot the cost of our pipeline with less file on the output. And finally, at this scale, Spark SQL is more efficient when it's run on Pocket files. If we compare the same query on CSV files and Pocket files, having the same data, the query run on Pocket files is 10 times faster than on gzip files. And basically, this leads to better performances for lower costs. How good is that? So of course, we have implemented that. And after some optimizations of the job with Pocket, here are some metrics shown previously after the optimization. We have divided by roughly 6 the amount of S3 files created. And Yeah, this metric does not really show the efficiency of the pipeline, but it can easily show the effect of having Parquet files compared to GZIP files. Also, in our test pipeline, we have voluntarily stopped. We clearly see that we code up pretty easily to reduce some delay between the moment logs are sent to S3 and the moment they are processed by our Spark job. We now use batches of 3,000 files instead of 10,000 files, which represent more time of logs processed for the same time spent to run the query on it. To have a clear comparison, I scaled this 3,000 batches metric to 10,000. And so for 10,000 Parquet files, we processed 15 minutes of data, where 10,000 GZIP files represent 48 seconds of data. And for me, I'm amazed to see how a simple file format change can improve the security of a company. So yeah, we have a great pipeline where we can catch up, but the next step of VPC Flow Log is to have them in Datadog. We want to be able to use the power of the product. By having logged into Datadog, we could run detection using Cloud SIEM service at the intake time, have efficient enrichment table, relations with other services, and more. We will be able to query some suspicious IP directly into Datadog and leak these IPs to other services that could have been compromised by the same IP. And of course, retrace the whole path of an attacker through the system. Also, since the Log4j vulnerability, other teams have shown some interest of having this data into Datadog. That's why we will soon use Datadog to detect threats using network traffic flows of Datadog. I think I'm good with the presentation.
Thanks, Théo. So I just want to clarify like one thing there in case anybody joined late as you're going through the performance optimizations. For everybody that doesn't know, Parquet is a file format that's really, really popular in data science, and we're just seeing it pop up in cloud native stuff kind of as a recent trend. A lot of services now can natively store data in Parquets, and that's really, really useful. And that time window that we were showing that went from like 46 seconds to 960 seconds, that's the slice of time that we're looking at in terms of the traffic, right? So it's the time range.
Yep, 10,000 GZIP files in our first pipeline is representing 48 seconds of logs. And now that we use for 3,000 files, scale to 10,000 for comparison is 15 minutes of data. So yeah, that's a huge improvement of our pipeline, since we can process more data. If we have some delays due to an issue in our pipeline, then we can catch up really easily and really fast.
I think one of the things also about this architecture that may be a little bit hard to understand if you're kind of new to this event-based architecture where you're monitoring logs in AWS is that just because a VPC generates a file of flow logs, the amount of flow logs in a single file is going to be variable based on the amount of traffic that was exchanged during that period. So you might get 10,000 files and they're all going to be different sizes, right? Because you get a file every 10 minutes, regardless of whether there was traffic logged or not. There almost always is, though. Got one question in the chat here, which I'll go ahead and answer, which is, does it work with GCP Flow Logs? And the answer is the Datadog product, of course, works with every cloud provider's native flow logs. And you can, of course, ingest those to Cloud SIEM and decide to alert accordingly. this is an AWS native architecture here for this presentation that specifically is focused on AWS Flow Logs. I have a few questions though for both of you, like based on some of what we just saw. The first of which is when we talk about performance, what is the criteria that you would use for kind of deciding when is it time to scale the number of shards for that Kinesis stream? So you talked about like 10,000 is a number that we're kind of pulling off there. Would that be kind of the tipping point if you needed to be able to query more than 10,000 records at a time?
Yeah, so each shard actually has a limit of what throughput it can serve. So once your data scales to an extent where you cannot where you can reach that max throughput limit, then it's time to create a separate shard. So we have a monitor set up, for example, that observes when we're close to reaching that limit, and if we're like 70% there, then we would open another shard, add another shard.
Thanks. Yeah, and I think this was a great introduction to just like opportunities to include stream processing for anybody that hasn't really seen Kinesis in an architecture before. Like Kinesis versus SQS is always kind of one of those architecture debates that you have with yourself when you're setting things up. And I think you made it really easy to understand that whole Kinesis flow with the sequence numbers and the dynamo tables. But if anybody from the audience has a question about any of that, please definitely let's surface those questions in the chat. But unrelated to that, you mentioned Misp, this threat intelligence platform. You mentioned it's an open source project, but for our audience, some folks may not come from a security background. How does Misp know what the indicators of compromise are?
Yeah, so as you said, it is open source and it comes from a variety of sources. So other companies can publish known IP addresses to that, and then Misp maintains these lists that you then also have access to. So it is this platform to collect them from different sources.
Awesome.
And you can also add your own, like when you maintain your own Misp instance, you can add your own individual IP addresses that you might want to maintain, but aren't necessarily publicly shared.
Yeah, I've seen some companies do that for like watch lists for threat actors, where if they start to get alerts for a specific IP in their SIM, they'll add a threat actor to their like internal watch list because they want an alert anytime that actor makes another move. So that's one of the more interesting use cases I think I've seen for those custom threat lists. Another question about the addressing. Do you also match against the CIDR blocks, like the class lists ranges with the slashes, or is it just individual IPs? Yeah,
right. So I kept 2 IPs to keep simple, but you can also add CIDR blocks. So in case people don't know, CIDR blocks are essentially a range of IP addresses, and that is actually pretty difficult to query efficiently to check whether an IP address is in that CIDR block. And we have a pretty interesting solution for that, where we use a segment tree, which is a binary tree holding ranges, these CIDR block ranges essentially, where we can efficiently check whether an IP address from the flow logs is included in one of the CIDR blocks from the Misp list.
Yeah, it's that in and of itself is a really interesting engineering problem to solve. And anybody that's ever done any sort of matching of addresses to CIDR ranges, I'm sure understands this, because the libraries off the shelf are saying like, is this in this set? Like based on how we do IP version 4 can be pretty cumbersome in code. We could spend a whole Datadog on session on just that, I'm sure. Yeah. Super interesting. So there's no new questions that have popped into the chat, but I think the final question that I have today is, do either of you have any guidance for folks that are brand new, maybe to VPC Flow Logs in general, that would be a great place to start? And, if there are folks that are watching this that are Datadog customers, is this something that they can do today inside the Datadog platform?
So yes, of course, you can do that on Datadog. And if someone wants to get started with Datadog, I would suggest to start manually by creating a VPC Flow Log setup from a VPC to, for example, a CloudWatch log group where you can see directly logs into the AWS console, or to S3 and then download the file. And then you can start from there to play with logs, reading a few things about that. There are a lot of documentations about that on the internet. And yes, of course, you can do that on Datadog by doing a bit of work, because that's quite an unusual setup, but yeah, you can do that.
Yeah, and I think my 2 cents is just to emphasize the fact that to start small, these VPC Flow Logs can get quite large in scale, and therefore start with one account or start with one VPC and collect the logs, look at them, and then scale up to really collect all of them.
I think one of the hardest things that you run into in the wizard is actually that first checkbox that comes up that's like, do you want to log only inbound traffic or outbound traffic? What would your advice be there?
Just like I said in previous slides, the more there is something really important about outbound traffic, because it means that you could have been compromised, especially if you are a public company that can be reached by everyone. So yeah, inbound traffic is great. It's important to monitor it. And if you want to have a first milestone after you have scaled up to all of your VPCs, I would suggest to first go with outbound traffic if you want to have an efficient monitoring system with VPC Flow Logs. Then you can do the same thing for inbound traffic, of course.
All right. So with that, I think that we're all out of questions for today. Thanks, Théo, Anna, for being with us today, and the great presentation on detecting threats using network traffic flows. With that, we'll go ahead and wrap up this session of Datadog On.
Thank you.
Thank you.